Good morning, Cassie, and thank you everybody for tuning in. So I was asked to talk about the geological record of ocean acidification to give a little bit of a perspective over what we're doing today with our increasing carbon dioxide levels in the atmosphere. But before I do that, I wanted to give an introduction into what ocean acidification really means. So we all know that the levels of atmospheric carbon dioxide in the atmosphere are increasing, and you have all heard about the problem of atmospheric carbon dioxide and global warming. But in addition to global warming, the carbon dioxide in the atmosphere will also dissolve in seawater. And you can see that over here on the screen on the left-hand side. The carbon dioxide will not only dissolve in the water, but it will actually react with water, and it will form aqueous carbon dioxide, and that will then dissociate into carbonic acid, bicarbonate ion, and carbonate ion. And so while organisms in the ocean are interested in the presence of carbonate ion and bicarbonate ion for secreting their shells, the increased abundance of carbonic acid actually forms a problem. And it turns out that the more carbon dioxide we dissolve in the water, we're actually taking away the carbonate ion concentration in the water, and will turn it more and more into carbonic acid. And that is a problem in the ocean. And so when we're looking at this, we're really interested in the hydrogen ion concentration in seawater, which will increase when we have more carbonic acid in the water, and that will make the water a little bit more acidic. And what that means is that with the increased hydrogen ion concentration, that is measured as the negative decadic logarithm that tells us the pH. So when the acidification increases, when we have more hydrogen ions, the pH will actually go down. So now the organisms, as I mentioned before, they are indicated in, they're interested in the presence of carbonate ion in seawater. These are pictures of planktic snails that have been grown under controlled conditions in the laboratory. On the right-hand side, that is a shell that is grown under normal modern conditions. And then the further left you go, it shows shells that were grown under acidification conditions that we expect for the end of this century. And the more time they spent in that water, the more dissolved these shells became and the more malformed they became. And these are specifically planktic snails, and you may have never heard about them or never looked at them. They're actually very pretty. But these organisms are important because they're important parts of the food chain. So for instance, these snails are often eaten by Pacific salmon, and so if you imagine that these shells now have, or these snails now have thinner shells, they're more vulnerable to predation by all kinds of organisms, and therefore they might disappear in the future, and that might take away some of the livelihood of the Pacific salmon. To put this all into perspective, this figure over here shows you a timeline. On the top you can see from 1900 to the year 2300. And we see three panels. The top panel is carbon dioxide, the middle panel is surface temperature of the ocean, and at the bottom panel you can see the sea surface pH. And the red lines and the blue lines, they indicate what we call representative concentration pathways that were used by the Intergovernmental Panel of Climate Change. And it looks at concentration pathways or emission scenarios until the year 2100, and these values 8.5 and 2.6, they actually relate to what kind of warming we might have at that time, or what the radiative forcing would be. These are not numbers in temperature. But you can see that the carbon dioxide from the year 1900 until the year 2000 has actually already increased by about 40%. And by the year 2100, if we follow the most extreme concentration pathway, then it might go up to somewhere near 1,000 parts per million. If we stay at modern levels, then it will still be 40% higher than what we have seen in pre-industrial times. Now, when you look at the middle panel, you can see the associated warming with that, so the well-known problem of global warming. On the bottom panel, you can see the pH changes. And so from the year 1900 on the left-hand side to the modern, we have already dropped pH by about 0.1 pH units. And with the most extreme concentration scenario, we might drop that by another 0.3 to 0.4 pH units. 0.1 to 0.3 may not sound very much, but because this is on a logarithmic scale, this actually means quite a lot in terms of acidification. So we're really talking about acidification or increase of hydrogen ion concentrations by about 30% until today, and this might actually increase, or it might double by the end of this century, and that is a big problem for marine organisms. And so that is actually shown on this slide. On the right-hand side, you have the modern conditions, or the more basic seawater conditions. On the left-hand side, in red, you see the more acidic conditions that we're expecting for the end of the century. And these are different pictures of organisms that have been grown under these different conditions. I've already shown you the snails on the bottom. On the right-hand side, you can see a tile that was put into a coral reef under modern pH conditions, and you can see it's very colorful, so little corals have grown on that. If you put the same tile into conditions that we're expecting for the end of the century, then you see that it's mostly overgrown by algae, so the corals cannot grow under those conditions. In the middle panel, we can see coccolithophores. These are planktic calcareous organisms that, again, form part of the bottom of the food chain. And on the right-hand side, you see the pristine shells that were grown under normal conditions. On the left-hand side, you see the more malformed when they're growing under conditions that we're expecting for the end of this century. Similar on the left-hand side, there's an actual snail that is pitted that is not that has not the same shell that it would have under normal conditions. So many of these organisms you may not care about, but as I mentioned before, they do form the bottom of the food chain, and so therefore they can have repercussions into our food system. So as I mentioned in the beginning, I am not actually working on these modern acidification problems. This is what the following two speakers will be talking about, but I wanted to look into the geological record of ocean acidification. And what you can see on this slide is a 300 million year record of diversity of different forms of calcifying organisms in the oceans. At the bottom, we see shallow reef builders like corals, and we have some foraminifers. Those are organisms that we use a lot in paleoceanography. And then again, some of those calcareous nanofossils like the coccolithophores that I showed you in the previous slide. The reason why we're doing this is because in the previous slide, I showed you all kinds of organisms that are affected by acidification, but it actually turns out that not all organisms are affected in that way. And so it makes it very difficult for us to predict where the ecosystems are going in the future. By looking into the fossil record, we can look at what happened to these organisms in the past when they may have been affected by ocean acidification. And these diversity trajectories, so that means the blue lines and the black lines, they indicate by thickness how many species there were present at any given time in Earth history. And so the thicker the line is, the more species there were. The thinner the line is, the less species there were. And so the vertical red lines over here, they indicate actual mass extinction events, starting 250 million years ago with the Great Dying at the end Permian, 200 million years ago at the end Triassic, and we had a couple of oceanic and Arctic events, the well-known extinction of the dinosaurs that happened with the asteroid impact at the end of the Cretaceous, the Paleocene, Eocene thermal maximum 55 million years ago, of which we don't really know what caused it, and then the last deglaciation when a lot of carbon escaped from the ocean and acidified the surface ocean. And so these little pictures that you can see on top of this, they indicate the potential causes of acidification, like massive volcanism at the end Triassic and Permian, the asteroid impact. At the PETM, there may have been methane hydrate release, or there may have been permafrost thawing and other events. But you can see that many of them actually made those diversity trajectories thinner, meaning that there was extinction at that time. And that is the reason why ocean acidification has been considered as a potential cause for these extinction events. So we wanted to understand whether that is really true and whether we can say that acidification really caused these extinctions. But in order to do that, we cannot hold a pH meter into the ocean because it will not tell us what the pH was 300 million years ago. So what we're doing in geochemistry is that we are actually using proxies. And proxies are so-called stand-ins or surrogates for environmental parameters that can no longer be measured directly. And to compare that to what we're doing today, or to give an example of what a proxy might be, is if you imagine you don't have a thermometer and you're trying to find out how warm it is outside, you would look out of the window and infer from what other people are wearing whether it is warm or whether it is cold. Now our proxies, our geochemical proxies, are a little bit more sophisticated than that, and I do not have the time to go into all the details. But what I can tell you is if we have higher carbon dioxide concentrations in the atmosphere, so if you look at the red values on the left of this screen, higher carbon dioxide in the atmosphere means that we will dissolve more carbon dioxide in the water. That means the pH will drop, and this drop in pH will actually be recorded in the boron isotopic composition of planktic organisms like these foraminifer shells that you can see over here. The boron isotopic composition is given in delta 11b. This value will decrease when the pH is low, and it will increase when the pH is higher. So on the right-hand side is a condition where the carbon dioxide in the atmosphere is low. That means less carbon dioxide in the water. higher pH and therefore higher boron isotopes. Now these plankton shells at the end of their life cycle will sink to the bottom of the ocean. They will litter the seafloor. We can take sediment cores out of that seafloor, then pick those fossil foraminifer shells out of it, analyze their boron isotopic composition, and then infer what the pH and the carbon dioxide of the seawater was at the time, and therefore we can say something about the carbon dioxide in the atmosphere. To give you an example of how this might work, we can look at the last 400,000 years. So these wiggly lines over there give you several different records of carbon dioxide in the atmosphere that was measured in ice cores. So the pictures on the top left show you ice core pictures, and then this is a slice of an ice core that shows you the gas bubbles that were trapped in that ice that contain old ancient air. And so you can see that over the last 400,000 years, the carbon dioxide levels were going up and down about every 100,000 years. Before the industrialization, the carbon dioxide levels were at 280 parts per million. We have now increased that to about 400 parts per million. But what we're interested in is what is the acidification of the surface ocean as we're going from an ice age about 20,000 years ago, for example, into the pre-industrial. And so the picture on the top right shows you a map of the oceans that actually shows you a pH map, but what you really only care about is that little dot over there that indicates ODP 668. That is a sediment core that I have analyzed for this. And I analyzed these planktic foraminifer shells that are shown below. And you can look at the pH that we inferred from the boron isotopes that indicate that the pH during the last glacial was about 0.15 pH units higher compared to the pre-industrial. So from all kinds of evidence and other proxies, we can say that during the deglaciation, that means from the transition from the ice age 20,000 years ago to the pre-industrial, the surface ocean warmed by about 2 to 3 degrees Celsius. The pH dropped by about 0.15 pH units. And we did see calcification changes in these planktic foraminifers. They actually grow thinner shells today compared to what they grew in during the ice ages. But what is important is that for this transition to happen, it took about 6,000 years. And so if we try to compare the pH change at that time to the pH change that we're expecting over the current century, then the pH change at the time was about 0.002 units per century. And remember what I said in the beginning, the current pH change is somewhere on the order of 0.1 to 0.4 units per century. So what we're doing today is much, much larger than what happened at the end of the last deglaciation. And so therefore we went to a much larger event, and that is the Paleocene Eocene thermal maximum. That was an event that happened about 56 million years ago. And what you can see here is a map of sediment cores that have been studied for this. It was a global event that has been found everywhere in the ocean and also on land. These are some records that I have worked on. But what is important about this event is if you look at the figures below, they show sediment cores. And these sediment cores were taken at this location of Namibia in the South Atlantic, where you can see ODP 1263. That's one of those cores. And what you can see is that these sediment cores actually change color from the bottom to the top. And that is how time proceeds. So you can see that at the bottom, they were light in color, and that indicates calcium carbonate deposition at the seafloor. And then all of a sudden, they turned brown. And then they slowly recovered again to a lighter color. This change into brown actually indicates that all the calcium carbonate at the seafloor was dissolved at that time, and it was replaced by clay deposition. And so that is an indication that the PETM was associated with a massive input of carbon dioxide. And in addition to that, it was also, so that created dissolution in the ocean, but it also acidified the surface ocean to a degree that we can actually see changes in the ecosystems. So on the right-hand side, you see a figure that shows a sediment core that was located close to ODP 1209 in the Pacific Ocean. And again, you can see the color change from light color to brown color. But you can also see plankton samples from these sediments that have been washed. And you can see they were large before the onset of the PETM. During the PETM in the middle, we can actually see dwarfism of these species. There are even different species in there that occurred only during that event. And then when you look afterwards at the top of that record, you can see that they're larger again, and now they're actually different species than they were before the event. So that is an indication that we had extinction at that time. We had dwarfism, we had changes in the ecosystem. So we wanted to find out how large the acidification actually was at that time. And so we went into ODP 1209 in the Pacific Ocean, and these are results of geochemical analyses that we produce from these planktic foraminifer shells they can see on the right-hand side. Without going into much detail, what you see here is a timeline again. 0 indicates the PETM, or the onset of the PETM of that carbon perturbation, and time goes from right to left. So the part right of it is older than the PETM, and the part left of it is younger than that. On the top panel, you can see carbon isotopes, delta 13C. And the fact that they drop into the PETM and then slowly recover is an indication that we had an input of carbon into the system. The middle panel shows you magnesium-calcium ratios in all 3 species. And when magnesium-calcium increases, that is an indication for warming. So as we had more carbon dioxide in the system, we also warmed the planet. And this warming is somewhere on the order of about 5 degrees Celsius, or about 9 to 12 degrees Fahrenheit. So it warmed, and then afterwards it recovered, so it dropped down again. On the bottom, you can see boron isotopes. And as I told you before, when boron isotopes decrease, then that is an indication for acidification. And we can see that at the same time when the carbon isotopes and the magnesium-calcium show changes, we also see a decrease in the boron isotopes. Now, when we try to translate this into seawater pH, we can see that this change in boron isotopes indicates a pH drop on the order of 0.3 pH units. So this is similar to what we're expecting by the end of the century, but again, we have to put this into perspective, and we have to look at how long it actually took to get there. So what happened at the PETM, we had warming on the order of 5 degrees Celsius, pH dropped by about 0.3 pH units. We had ecosystem changes like extinction, dwarfism, changes in the species composition, but it actually took 3,000 to 5,000 years for this event to happen. And so if we calculate what the pH change is per century, then we're still an order of magnitude slower compared to what we're doing today. So again, today was 0.1 to 0.3 pH units per century. At the PETM, it was only 0.01. So that really puts it into perspective, that what we're doing today really outpaces essentially everything that we've done in Earth history. And so that makes it so special. Now I wanted to give you one last event, or one last situation, and that is one that many climate skeptics often use as an indication for carbon dioxide not being such a big problem, or acidification not being such a big problem. And that timescale that we're talking about is the Cretaceous. And during the Cretaceous, we know that it was very, very warm. The carbon dioxide levels were probably as high as 1,000 parts per million, or even higher than that. And yet, we have these chalk deposits that were deposited at that time in the Baltic Sea surrounding England and also Germany and other locations. So massive calcification that happened at a time when the carbon dioxide levels were very high, and obviously the pH of the ocean must have been very low. So what is going on at this time, and why were these organisms able to secrete their shells at that time? The reason for that is that the Cretaceous was a time when the carbon dioxide levels were high for millions of years, for actually tens of millions of years. And what happens on these very long time scales is that the high carbon dioxide levels, they will actually cause weathering of rocks on land, as you can see on this image over here. So weathering of rocks on land actually brings the same elements that organisms want to secrete their shells, the calcium and the bicarbonate ions and carbonate ions, back into the ocean, despite the fact that the pH was low. And so if they have those elements in the ocean, they can calcify, and therefore they could secrete these massive chalk deposits that we can marvel at today. So to bring this to an end, what we know about ocean acidification in Earth history is that it has occurred. It left evidence in the form of interrupted carbonate deposition, reef crises, extinction among marine calcifiers. We know that it goes together with warming and changes in the dissolved oxygen concentrations and nutrients, and in that regard it makes it very, very similar to what we're doing today. And so we can use them as potential analogs, but it turns out that this current rate of carbon dioxide release that we're observing today and the oceans respond, that they're really unparalleled in Earth history. And with that, I would like to hand it back to Cassie. Thank you so much for your attention.